Electronic Devices, Junction Diodes, Part 3, Series on Semiconductor Devices and Circuits, Lecture number 2.13. PN junction diodes or semiconductor diodes. These are two-terminal, non-linear, unilateral devices, and they use semiconductors, extrinsic semiconductors, for their fabrication. In the present session, the focus is on their resistance and also on their capacitance. Diodes, junction diodes, under forward bias exhibit very small resistance and under reverse bias exhibit very high resistance. Apart from resistance, they also possess certain capacitance. Under forward bias, they have certain capacitance, usually a large amount, and this capacitance is called diffusion capacitance. Under reverse bias, also they exhibit a capacitance. It is a smaller one and it is called transition capacitance. Because of low resistance or high resistance nature of the device, the current also sometimes it is high, sometimes it is low. All the three aspects so far mentioned, resistance, capacitance, and current through the diode. These three aspects, they are covered in the present session. Now let us move further to begin to start the course session. The session is started with resistances, diode resistances. For any electrical or electronic device, two types of resistances can be defined. One is called static, another is called dynamic. So static resistance, dynamic resistance. Two types of resistances can be defined for any electrical or electronic device. The static resistance, usually indicated by capital R of a diode, is defined as the ratio of V to I ratio or voltage to the current ratio. The current passing through the diode and the voltage across the diode. V to I ratio. That is static resistance. Static resistance varies widely with the V and I, voltage and current, and it is not a useful parameter. What does it mean? At small voltages, the device exhibits one static resistance. At higher voltages, it exhibits some other resistance. At moderate voltages, it may be something different. So, resistance, static resistance, it varies widely with applied voltage. In the same way with the current that is flowing through the device. Because of this variable nature, varying nature, it is not a useful parameter. Under forward biased condition, usually it is denoted by RF. For a diode, under forward biased condition, usually it exhibits very small resistance. It is indicated by RF, capital RF. And under reverse biased conditions, it is denoted by RR, capital R, small r. Capital R indicates that it is static resistance. Small r indicates that it pertains to reverse biased condition. Small f indicates that it pertains to forward biased condition. After static resistance, we consider dynamic resistance. The dynamic resistance, usually indicated by small r, is a more useful parameter for small signal operation. Notice its importance lies in the fact that it is best suited for describing the functioning of diode for small signal operation. So usually we consider dynamic resistance of the diode more frequently in the analysis. By definition, the dynamic resistance of a device is the ratio of incremental voltage across the device to incremental current through it. It is not a constant, but it depends upon the operating voltage. When it comes to variation with the operating voltage, dynamic resistance is no better than static resistance. On that count, both are in the same disadvantaged position. Now, a few points regarding dynamic resistance of a device. It is the ratio of incremental voltage across the device to incremental current to it. Now, to understand dynamic resistance, you consider a device. It may be diode or something else. Let us suppose applied voltage is V and current flowing is I. If you consider the ratio V to I simply, then it is static resistance. To understand the concept of dynamic resistance, you consider that voltage, applied voltage across the device has been increased by an amount delta V, let us say delta V. Because of increase in applied voltage or voltage across the device, naturally current also changes. Let us suppose increase in current is delta I. Now delta V by delta I, this is called dynamic resistance, incremental voltage to incremental current ratio, dynamic resistance. After having this understanding, we consider dynamic resistance of a diode, PN junction diode. As already mentioned, by definition, dynamic resistance small r is delta V by delta I in the limit delta I, delta V, when they become very, very small, we can say delta V by delta I is equal to dV by di. Now with this definition, we try to determine dynamic resistance of diode. Consider diode equation and differentiate it on both sides. This is diode equation, I equal to I naught e power V by eta Vt minus 1. Now differentiating di left side, right side, I naught e power V by eta Vt by eta Vt dV. A little bit of manipulation gives us dV by di equal to eta Vt by I naught e power V by eta Vt. Now we consider forward biased situation. Then we consider reverse biased situation. Now one can notice I naught e power V by eta Vt. This can be expressed as I plus I naught from this equation. This is I naught e power V by eta Vt. This is equal to I plus I naught. So R equal to eta Vt by I naught plus I in general. But under forward biased condition, I is large when compared to I naught. So I naught can be neglected. So it results under forward biased condition, dynamic resistance becomes eta Vt by I. This is forward resistance or resistance of the diode under forward biased condition. Under reverse biased condition, the expression remains as it is. We cannot do any further manipulation. So before going further, note dV by di, dynamic resistance of the diode is eta Vt by I naught e power V by eta Vt. This relation is valid both for forward and reverse biased situations. In case of forward biased diode, it becomes equal to eta Vt by I. In case of reverse biased condition, it remains as it is. After discussing about resistances of the diode, now we spend some time discussing about diode capacitances. Junction diodes are associated with capacitance under both the biased condition. Forward biased condition, reverse biased condition, in both the conditions, in both the situations, capacitance exists. Under forward bias, they exhibit large capacitance called diffusion capacitance. Accumulation of minority carrier charge is responsible for this capacitance. Transition capacitance appears across the junction when it is under reverse biased condition. Uncovered impurity ionic charge is source of this capacitance. Note, under forward biased condition, diffusion capacitance exists. Under reverse biased condition, transition capacitance exists. Accumulation of minority carrier charge is responsible for diffusion capacitance. Presence of uncovered impurity ionic charge is responsible for transition capacitance. These 2 points are basics, fundamentals regarding the capacitance of PN junction diodes. Out of the two, quantity wise, first one is very large compared to the second. Varactor diodes make use of transition capacitance, provide variable capacitance. Actually, in this point, there are two sub-points. First sub-point is diffusion capacitance is large when compared to transition capacitance. This is one point, one sub-point. Second sub-point is varactor diodes use transition capacitance, not diffusion capacitance, to provide variable capacitance. Now, some points regarding transition capacitance. In the depletion region, there exists a charged dipole with the positively charged donor ions in the N side and negatively charged acceptor ions in the P side. So this is diode. This is the interface. Let us say this is a P region, this is N region, this is junction region. In the junction region, there exists negative ions, P side. Here, N side, positive ions. These ions, columns of ions, they are the source, they are the origin of transition capacitance. The magnitude of this charge varies with applied voltage, leading to a capacitive effect. This component of capacitance is known as space charge or transition capacitance. Transition capacitance is called as transition capacitance for the reason that it is there in the transition region. It is also called space charge capacitance, another name for transition capacitance. Formally, it can be defined as a ratio of change in the charge dq on impurity ions to change in the applied reverse bias voltage dV. Mathematically, Ct equal to dq by dV. One point one has to keep in mind is capacitance can be defined as Q by V also. But here the definition is change in charge to change in voltage. So this is the differential capacitance. If it were Q to V ratio, then it could have been static capacitance. But notice in electronics, most of the quantities are differential quantities, differential resistances, differential capacitances, differential gains. Almost all are defined under incremental or differential conditions. It can be shown that Ct is equal to epsilon A by W. For a step graded junction, epsilon stands for Permittivity of the semiconductor. Diode is made with one or other semiconductor. That semiconductor must be having certain permittivity. Epsilon corresponds to the permittivity of the semiconductor. A cross-sectional area, W width of the transition region. Here is explained transition capacitance. A diode is shown with the p-type impurities added on the left side and type impurities added on the right side. But notice in this case, p-type impurities concentration is very large when compared to n-type impurities. For this reason, the width of the junction on n side, it is very large when compared to width of junction on p side. You can see this is WP. It is very small when compared to width on n side. WP, WN. WP plus WN is W. The relation that has been given in the previous slide, that is CT equal to epsilon A by W, that relation pertains to this situation. Here situation refers to where one side of the diode is heavily doped when compared to the other side. Before going further, one point is required to be mentioned. In WP, there exists negative charge, ions, immobile ions. In WN, positive charged ions. Between them, capacitance. Now, the transition capacitance is defined under reverse biased conditions. Certain important points regarding transition capacitance. It is a voltage dependent capacitance. Notice that with the change in voltage, applied voltage, the width of the junction region changes. In general, with increase in reverse biased voltage, width of the junction region, it increases. If the reverse biased voltage is decreased, width also decreases. So the capacitance, as width of the junction region changes, capacitance also changes. So it is a voltage dependent capacitance. Its value decreases with increase in reverse bias voltage as the depletion region width increases with increase in reverse bias voltage. Similarly, for an increase in forward bias, the width decreases and the capacitance increases. Here one point requires to be mentioned. Transition capacitance mainly exists or dominant when the diode is under reverse bias. When the diode is under forward bias, it is the other capacitance, that is a diffusion capacitance, which dominates, which is predominant, which influences the functioning of the diode. But the point is, transition capacitance exists in the diode even under forward biased conditions, and diffusion capacitance exists in the diode when the diode is under transition reverse biased conditions. However, under forward biased condition, transition capacitance is negligible, and reverse biased condition, diffusion capacitance is negligible. So small we can ignore their presence. But as a matter of fact, under forward biased condition, transition capacitance exists, and the capacitance increases with the increase in forward bias. We consider another type of capacitance, diffusion capacitance. Diffusion capacitance, it is indicated by CD. It is also known as storage capacitance. The minority carrier charge injected across a forward biased diode is a very strong function of applied bias. So what is this diffusion capacitance? Consider diode under forward biased condition, P side impurities on one side and type impurities on the other side. When it is forward biased, what happens? Holes are injected towards N side and electrons towards P side. Holes, when they enter into N side, they become minority carriers. So here minority carrier holes exist. Here minority carrier electrons exist. When holes travel towards the terminal of N region, what happens is they encounter plenty of electrons, and within a travel distance, a small travel distance, these holes can meet sufficient number of electrons to recombine, ultimately disappearing. So what happens is they cannot reach farther points, farther away points from the junction region. Holes exist only in a small region surrounding the junction region. Similarly, electrons. So a good amount of electrons exists on p side, good amount of holes exists on n side surrounding the junction region. So this negative charge on one side, positive charge on the other side, their presence leads to the creation of a capacitance, diffusion capacitance. The amount of charge near the junction, it is a very strong function of applied bias. The injected minority carrier charges in the region near junction with their associated voltage dependence contribute to a capacitance known as diffusion or storage capacitance. The origin of this larger capacitance lies in the injected charge stored near the junction outside the transition region. One can define it without much difficulty. Formally, it can be defined as the rate of change of injected charge with applied voltage, CD, equal to, by definition, dq by dv. Notice here also it is dq by dv, not q by v. As already mentioned, like CD is also differential or incremental capacitance. The source of diffusion capacitance is illustrated in this diagram. This is diode. It is under forward biased condition. So junction width becomes very small. Holes get injected to N side. See, plenty of holes, hole concentration. Electrons get injected to P side. Electron concentration. Notice hole concentration as well as electron concentration. It is falling as you move towards the terminal end. Falling. The fall is due to recombination. Consider holes here. Plenty of holes get injected into N side and they keep on traveling towards the terminal end. While traveling, they meet electrons. Plenty of electrons are available because it is N side. When they meet, recombination happens. When recombination happens, concentration naturally falls. So that's why hole concentration keep on falling. Rigorous mathematical analysis shows that the fall is exponential. So holes fall exponentially. In the same manner, electrons also fall exponentially. Electron concentration on p side. Notice good amount of negative charge is there on p side. Good amount of positive charge is there on n side. These two charges, minority carrier charges, they are the source of diffusion capacitance. Some more points regarding diffusion capacitance. For a diode heavily doped on one side with respect to the other, the diffusion capacitance is. Definition has been given in the previous slide. When we apply this definition to a diode heavily doped on one side with respect to the other, then one can show it is equal to tau. Tau means lifetime. Di by dv means G, conductance of the diode. So it is equal to tau multiplied by G, and in terms of current, it turns out to be tau I eta Vt. Vt is Einstein constant, 2 26 millivolts at room temperature. If the doping levels on both sides are comparable, then the expression for diffusion capacitance becomes CD equal to tau PIP of 0 plus tau N IN of 0 by eta Vt. Here is given now a table comparing diffusion capacitance with transition capacitance. Transition capacitance is dominant under reverse biased condition, whereas diffusion is dominant under forward biased condition. Transition capacitance is small in value, whereas diffusion capacitance is large in value. Transition capacitance is due to uncovered impurity ionic charge at the junction, whereas diffusion capacitance is due to diffused minority carrier charge at the junction. Ct is given by epsilon A by W, CD is tau G. Transition capacitance decreases with increase in voltage under reverse bias, whereas diffusion capacitance increases with increase in voltage under forward bias. Both are incremental capacitances or differential capacitance. Both exist under all biased conditions. Now, after discussing about resistance, about capacitance, now we move to current, diode current under current components. We consider the situations, forward biased situation, reverse biased situation separately. First, forward biased situation. When the diode is under forward biased situation, large current flows. When it is under reverse bias, small current flows. Under forward bias, the bias voltage directly appears across the junction, reducing the barrier height. Reduced barrier height further helps the carriers to move more freely to the other side, so resulting in huge amount of current. Hole concentration on P side and free electron concentration on N side increases. Due to the existence of concentration gradient, injected holes start diffusing towards N side and electrons towards P side. Important aspect is, under forward biased condition, barrier height comes down because of the existence of concentration gradient. Holes start diffusing towards N side and electrons starts diffusing towards P side. So it is diffusion that plays important role in driving current through the diode under forward biased condition. Now we consider reverse biased condition. The bias voltage directly appears across the junction, increasing the barrier height. Increased barrier height further restricts carrier movement towards the other side. In earlier case, it is a reduction in barrier height. The present case of reverse bias, it is increase in the barrier height. When barrier height becomes large, current further gets restricted. Hole concentration on P side, free electron concentration on N side falls down due to existence of potential gradient across the junction. However, thermally generated holes drift towards N side and electrons towards P side in the junction region. Under reverse biased conditions, small current flows. What is the source of that small current? Thermally generated electron holes in the junction region. They drift under the influence of potential gradient. This drift is responsible for the current, small current that flows under reverse biased condition. A few points regarding currents, internal currents. In the earlier slide, the discussion was about terminal currents. Now it is about current components, somewhat internal to the diode. Diode, PN junction diode, is a semiconductor device. Within semiconductor, there exists electrons, there exists holes. Travel of electrons they give rise to certain amount of current. Travel of holes also give rise to certain amount of current. Apart from this aspect, another aspect one has to keep in mind is electrons and holes. They can travel under the influence of potential gradient. In such case, it leads to drift current. They may travel even under the influence of concentration gradient. In such case, the resultant current is called diffusion current. So two types of charge carriers are there, two types of processes are there, resulting in four types of currents within a semiconductor device. As diode is a semiconductor device, here also in the diode also there can exist four types of currents. What are they? One current due to electron diffusion, another component due to hole diffusion, another component due to electron drift, another component due to hole drift. Here is shown a diode with the P region on the left side, N region on the right side. Electron diffusion happens from N to P side. Hole diffusion happens from P to N side. Electron drift happens from P to N side. Hole drift happens from N to P side. These diffusion and drifts, they give rise to currents, conventional currents. Electron diffusion results in conventional current from P to N side. Hole diffusion results conventional current from P to N side. Electron drift results in a conventional current from N to P side. Hole drift results in a conventional current from N to P side. Some more points regarding these currents we consider in the next slide. Before going further, notice in any diode, all the four currents exist, but their proportion need not be same all along the length of the diode. It varies. The proportion also varies with the impurity concentration. Some more points regarding current components. Electron diffusion current, JN diffusion, it is due to electrons diffusion from N to P side, and the direction of current is always from P to N side. Hole diffusion current, JP diffusion, it is due to holes diffusion from P to N side, and resultant current is always from P to N side. Electron drift current, JN drift, this current is due to electrons drift from P to N side, and it results in a current which is always from N to P side. Hole drift current, it is due to holes drift from N side to P side, and the resultant current is always from N side to P side. To understand the directions of carrier movement and resulting conventional current, one has to keep in mind hole is positively charged particle. If it moves rightwards, it results in a current, conventional current, that is towards right side. Whereas electron, if you consider electron which is negatively charged, if it moves towards right side, it results in a conventional current which is leftwards, opposite to the direction of movement of the electron. This aspect one has to keep in mind while trying to understand the directions of these four components of currents. With this, we come to an end to the session. Before closing down, let us recollect the important aspects that are considered in this session. To begin with, we considered resistance, dynamic resistance, and then dynamic capacitance. At the end, we consider various current components that exist inside a semiconductor diode. Hope this session is useful to you. We meet again in another session very soon with a topic, junction diodes, part 4.